Hello, students. Have you ever wondered how photographers, movie projectors, or even your own eyes know exactly where an image will form? Believe me, they don't just guess. Imagine if your camera said, "Oops, I'll just guess where to focus today." That would be chaos. Instead, optics gives us a reliable shortcut. This shortcut is called the principal rays. Think of them as the VIP light rays. No matter how many light rays enter the lens, these few always follow predictable paths. And once we know where these rays go, the rest of the rays politely follow the same rules and the image forms right where it should. Here's the beauty of it. Instead of struggling with detailed refraction at each curved surface, we only need to track three simple rays. That's it. Just three rays, and suddenly, like magic, the whole image appears in front of you. It's a bit like drawing a map. You don't need to sketch every tiny street in a city, just draw the main highways, and you instantly know how the city is connected. In the same way, principal rays are the highways of light through a lens, neat, predictable, and super useful. And here's the best part, once you master these rays, constructing ray diagrams becomes quick, accurate, and almost fun, like solving a puzzle with a guaranteed answer. So, ready to meet these three rays and see how they bring images to life. Alright students, let's start with the very first principal ray, the easiest one to remember. Whenever a ray of light travels parallel to the principal axis, the lens immediately knows what to do. For a convex lens, the ray bends and passes through the principal focus F on the other side. It's like saying, hey, if you're parallel, you've got a VIP entry straight through the focus. Now, for a concave lens, things flip. The parallel ray doesn't actually meet the focus, but it looks as if it's coming out from the focus on the same side. It's a bit like a magician's trick, the rays spread out, but if you trace them back, they appear to have started from the focus. Here's a classic real-life example, sunlight. All those parallel rays from the sun, when passed through a convex lens, converge at the focus. That's why you can use a magnifying glass to burn a piece of paper on a sunny day. Warning though, don't try it indoors with your spectacles, or you'll accidentally discover why ants don't like magnifying glasses. So remember, parallel rays always have a focus connection. For convex lenses, they meet at the focus on the other side. For concave lenses, they diverge but seem to come from the focus on the same side. Easy rule, but super powerful for drawing ray diagrams. Now, students, let's move on to the second principal ray. And this one is almost magical in its simplicity. If a ray is directed towards the optical center O of the lens, it doesn't bend, it doesn't twist, it doesn't do anything fancy. It just passes straight through, undeviated. Why? Because the tiny refraction that happens at the first surface is perfectly cancelled out by the refraction at the second surface. It's like two friends pulling you in opposite directions with equal force, you end up standing exactly where you started. The best part? This rule works for both convex and concave lenses. Doesn't matter if the lens is converging or diverging, a ray through the optical center always travels like it's on a VIP lane with zero deviation. And yes, there's even a neat formula note, the deviation, delta theta, equals 0 for a ray through O, or in simpler words, no bending, no problem. Here's a real-life example. Think about light passing straight through the middle of your spectacles. The central vision looks undistorted because those rays pass directly through the optical center of the lenses. If that didn't happen, every time you looked straight ahead, the world would appear wavy, like looking through a glass of water. So, Rule 2 is your best friend when drawing ray diagrams. Aim through the optical center and you get a straight, undeviated line every time. Alright students, time for the third and final principal ray, and this one is the mirror image of rule 1. If a ray of light passes through the principal focus F of a convex lens, it comes out parallel to the principal axis. Nice and neat, like reversing a process step by step. For a concave lens, if a ray is directed towards the focus before entering the lens, it emerges parallel to the axis after refraction. It's as if the lens says, if you aim for my focus, I'll straighten you out. Notice something interesting here. This is simply the reverse of rule 1, and that symmetry makes ray diagram construction super easy. Parallel rays go through the focus, and focus rays come out parallel. It's like the give and take of optics, fair and balanced. Here's a real-world connection. In optical instruments like projectors and searchlights, lenses are used to create beams of light that are perfectly parallel. That's why the light from a car's headlamp doesn't just scatter everywhere. The lens ensures it travels in a nice straight beam to light up the road. So, Rule 3 is your final shortcut. A ray through the focus becomes parallel to the axis. Simple, symmetric, and super useful. And with this, you've got all 3 principal rays mastered, enough to draw any lens ray diagram in seconds. Okay students, now that we know our 3 principal rays, let's put them to work. To locate the image of an object, you don't need to draw all possible rays. That would take forever. Instead, just apply any 2 of the rules we've learned. The point where those refracted rays meet, or where their backward extensions meet, gives you the exact position of the image. Now here's the exciting part. The nature of the image depends on where you place the object. Sometimes the image is real and inverted, sometimes it's virtual and upright, sometimes magnified, sometimes diminished. So yes, lenses can act a bit like mood rings. Their output changes depending on the input. Here's a quick formula reminder, the trusty lens formula, 1 by f equals 1 by v minus 1 by u. Where f is the focal length, v is the image distance, and u is the object distance. This formula is like a calculator's shortcut. It always confirms what your ray diagram shows. And for real-life connections, ray diagrams explain why cameras focus differently for near and far objects, why projectors can enlarge tiny slides into big screen images, and even why your spectacles correct your vision. So the next time you draw to rays and find an image, remember, you're doing the exact same physics that powers microscopes, telescopes, and even your smartphone camera. Alright students, time to roll up our sleeves and solve an example together. Because rules are nice, but examples are where the magic really sinks in. Here's the problem. An object is placed 30 centimeters from a convex lens of focal length 15 centimeters. Find the image position and its nature. Step 1. We start with our trusty lens formula, 1 by f equals 1 by v minus 1 by u. Step 2. Now substitute the values. The focal length f is plus 15. The object distance u is minus 30, negative, because the object is on the left side of the lens. So, 1 by 15 equals 1 by v minus 1 by negative 30. Step 3. Simplify that. Subtracting a negative becomes adding a positive. So we get 1 by 15 equals 1 by v plus 1 by 30. Step 4. Take the terms together. That gives 1 by v equals 1 by 15 minus 1 by 30. Solving that, 1 by v equals 1 by 30, which means v equals 10 centimeters. Step 5. So what do we conclude? The image is formed 10 centimeters on the other side of the lens. And its nature? It's real, inverted, and smaller compared to the object. Here's a neat way to imagine it. Place a coin 30 centimeters in front of a convex lens. The lens will form a sharp, smaller, inverted image of that coin on the other side, just like the diagram here. This is the principle behind projectors. A tiny slide of film creates a sharp but scaled image on the screen. So remember, by carefully applying the formula, plus signs and minus signs, and a bit of algebra, you can always tell where the image forms and whether it's real or virtual, big or small. Alright students, let's wrap things up with a quick summary of the principal rays. First, remember why we even bother with them. Instead of drawing dozens of rays and doing heavy calculations, we use just 3 special rays that behave in predictable ways. These rays are the shortcuts that make image formation in lenses simple and elegant. Rule 1. A ray parallel to the principal axis will pass through the focus, or, in the case of a concave lens, it looks as if it came from the focus. Like an express train that always knows its destination. Rule 2. A ray through the optical center goes undeviated. Straight as an arrow, because the tiny bends on both surfaces cancel out. It's like saying, why bother bending? Let's just walk straight through. Rule 3. A ray through the focus emerges parallel to the principal axis. This is just the reverse of Rule 1, and it gives a nice symmetry. Parallel and focus are like best friends exchanging paths. Finally, when we apply 2 or more of these rules together, the rays intersect, or appear to intersect, and that gives us the position of the image. From there, we can tell if the image is real or virtual, upright or inverted, magnified or diminished. So the big takeaway? With these 3 principal rays in your toolkit, you can draw accurate ray diagrams for any lens in seconds. And next time someone asks you how a projector, a camera, or even your spectacles form images, you'll have a neat, crystal clear answer ready.